So now that we've seen the definition of the Boolean product and we sort of better understand what it means to take the Boolean product of two general 0-1 matrices, we can now define the Boolean power of a single square 0-1 matrix. The rth Boolean power of A is the Boolean product of R factors of A, or R copies of A. It is denoted by A to the R with R in brackets, so as not to confuse it with the normal matrix power. Hence, you have that A to the R in brackets is A Boolean product with A, Boolean product with A, and so on and so forth. And we have R multiplications here. And this is well defined because we can show relatively straightforward that the Boolean product of matrices is associative, just like the normal matrix product. And what this means is that we can say the 0th Boolean product of A is just the identity matrix, which is the same size as A. The first Boolean power of A is just equal to A itself. And then for all R, it's going to be the R minus first Boolean power multiplied Boolean product by A itself. And this is where things get really neat, because we can consider our example from part 1, and if we go up to recall that example, the first example that we did of the power of the relation, we'll note something very nice. So let's look at this relation R. and this is a relation on the set B, one, two, three, four. The matrix that represents this relation R is a 0, 1 matrix with a 1 in the 1, 1 entry, a 1 in the 2, 1 entry, 0, 0, 0, and all the other entries, 0, 0, 0, and all the other entries, 0 in the 3, 1 entry, a 1 in the 3, 2 entry, and a 1 in the 4, 3 entry. And perhaps this will be a little bit easier to see if I rename 1, 2, and 3 as A, B, C, D. So this would be the relation A, comma A, B, comma A, C, comma B, D, comma C. You see that we can use 0, 1 matrices to represent relations. Namely, if you think of the rows as being each of the first element in our relation, and the columns as being the second element in the relation, or the ordered pairs from the relation, A, comma A is in this relation R. So we have a 1 in the row and column corresponding to A, comma A, and a 0 elsewhere because there's no other elements in this relation that start with A. Likewise, we have a 1 in the entry row 2, column 1, because B, comma A is in this relation and zeros are elsewhere. We have a 0 in C, comma A, or the row 3, column 1, because C, comma A is not in this relation, and so on and so forth, for each entry in this matrix. But this matrix MR represents this relation. If we consider the second Boolean power of this relation, MR, this is going to be MR Boolean product with itself, which, after computing using the procedure mentioned before, we get that MR second Boolean power is going to be equal to 1, 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0. computation of the third Boolean power is done by taking the second Boolean power and multiplying it by the first Boolean power. Which is this matrix right here. Boolean product, the original matrix itself. And when we compute this, we end up getting the following matrix. It's going to be 1, 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0. And it's relatively straightforward. You should go through and show that the nth Boolean power for n greater than or equal to 3 is always going to be equal to this m3, regardless of regardless of the n value. You can do this a number of different ways, but the idea here is that this is a very, very important thing to see right here, because if you consider the join of each one of these Boolean powers, so m r 1 or m r 2 or m r 3. So this is the OR operation of this matrix with this matrix or this matrix. You get a new matrix, 1 0 0 0 1 0 0 0 1 1 0 0 1 1 1 0, which is generated by some relation R star. The relation R star has A comma A in it, B comma A because of this one, C comma A, C comma B because of this one, D comma A, D comma B, and D comma C. In fact, if you remember one of the examples from the beginning of composition, And this relation is exactly what we found to be the closure relation, the transitive closure relation for the relation R that this matrix is coming from, where I've translated from the notation used in the other example, which was 1, 2, 3, 4, to just A, B, C, D, because I think it kind of better shows what exactly we're doing here with the relation. But you can very clearly see that this closure that we calculated before using powers of the relation that we defined is exactly the same as the join of the powers of the matrix that represents this relation, right? So right, this R star is directly represented by MR star, which we calculated by taking the Boolean powers of the original relation MR and then joining each one of these powers together. Not only that, but we also find that for each one of these Boolean powers, the matrix that represents the power of the relation is the correct matrix for representing that power of the relation itself. So for example, we know that MR, the matrix, the 0, 1 matrix representing R, we calculated as MR. This is the relation and the 0, 1 matrix column. It represents the relation. So MR is the 0, 1 matrix that represents R. MR Boolean power 2 is the matrix that represents R squared for the second power of the relation R. MR3 is the matrix that represents the third power of the relation. And MRN is the relation that represents the nth power of the relation. And because right, this power of the relation stops changing at 3, we also have that MRN is equal to MR3 for all n greater than 3. But in general, we're not guaranteed for this to happen, so we have to be careful when we're talking about this. And I will be a little bit more specific a little bit later on when we officially define the transitive closure of a given relation. But this is a very, very cool connection, and it immediately gives us a method for calculating the connectivity in a relation. And it turns out that this is directly related to connectivity in a graph, which is extremely important for measuring concepts like data flow and how connected a given relationship is. I can't overestimate the many applications of this idea. Not only that, but there is this beautiful connection between linear algebra, so some basic, relatively basic concepts in linear algebra, and this concept of mathematical relation between sets. And I want to note that the actual connectivity relation is we have infinitely many joins here as well as infinitely many unions here. The only reason we only have 3 here is for this example is special and kind of peters out after the third term. The nth power of the relation is the same as the third power of the relation. So by the nature of this union, we don't have to compute any more powers. But in general, this is not the case. So don't be fooled. Right? You have to, in general, for each different problem, think of this. Unless you prove otherwise, you have to think of all of the different power. A proof of the connectivity relationship is for the union of all of the powers of R. The if and only if statement that we proved before justifies this idea because it has to hold, or the relationship between transitivity and the powers of a relation holds if the nth power relation is a subset of R for all n, for any value n. The relation is transitive if and only if the nth power of the relation is a subset of the relation itself for all values of n. So in general, right, we have to check all values of n and take the union of all values of n in some sense, all powers of R, in order to ensure transitivity. Nevertheless, this is a very, very good example for explaining what we'll be doing a little bit later on, which is forming what's called the transitive closure of a given relation. Before we do that, I want to touch on a couple more examples related to the join and meet. Defined before, can be used to express, and are used to express either set intersection and union. For a given relation, for two given relations. For example, if R1 and R2 are two separate relations on the Cartesian product of A cross B, then the matrix representing R1 and R2 is simply the join or and operation between the matrices representing each individual set, or each individual relation, and the matrix representing R1 union R2 is the meet operation between the matrix representing R1 and the matrix representing R2. So this justifies what we talked about before in terms of the transitive closure of a relation. We'll make this formal a little bit. But let's just go over one example of this to make sure that we're all following along. If we have a matrix A, or the relation on a set A and a set B, say R1 is one relation, it's the relation AA, AAE, AF, CE, CF, and R2 is the relation A F A E C F B E the matrix that represents R1 is going to be 3 by 2 and it's going to be the matrix 1 is AE is in the relation, AF is in the relation, there's no B, so no value with the starting value of B, and then CE is in the relation and CF is also in the relation to R1. The matrix representing R2 is going to be AF, AE, BE, and CF. MR1 meet MR2 is the OR operation. The bitwise OR should be 1 1 1 0 1 1, and the join operation, the bitwise AND, this is going to be 1 1 1 and 1 1 and 1 0 and 1 0 0 and 0 0 1 and 0 which is 0 and 1 and 1. And if you look at these two matrices and you think of what the intersection of these two relations or these two sets of ordered pairs is, and the union of these two ordered pairs is, you'll see that what we get for the intersection and the union is exactly what these matrices are giving us. This matrix is saying that for the union, AE, AF, CE, and CF and BE are all elements in this relation, which is exactly the union. And similarly, for the intersection, R1 intersected with R2 should be AF, AE, and CF. So this computational procedure is exactly giving us what we want and what we expect. So this matrix that we got by calculating the join of the two matrices representing R1 and R2 is identical to the matrix representing the intersection of these two relations. And likewise, so this matrix is the same matrix as representing the union of these two relations. And hopefully you can clearly see now what is meant, right? We have this direct connection between these 0-1 matrix operations and the resulting set theoretic operations of union, intersection, and even composition. We've already seen how to represent the power of a relation on one set as a square 0-1 matrix, but we can do this for arbitrary relations on finite sets A, B, and C, and the composition of two different relations. Specifically, right, suppose that A, B, and C are finite sets, and that R is a relation from A to B, and S is a relation from B to C. We can represent relation R by a matrix MR and specifically let's suppose that the cardinality of A is M, cardinality of B is K, the cardinality of C is N. This matrix MR is going to be an M by K matrix, and we can represent S by A K by N matrix. Each of these are 0, 1 matrices. We have that the matrix that represents the composition of S with R is going to be exactly equal to the matrix R Boolean product with the matrix MS. And to see this, let's look at the example from the beginning of the composition. So the very beginning of when we started talking about composition. And I've translated this example to using letters instead of numbers, just to show you that the type of these sets in the ordered pairs is rather irrelevant. So this is from a set with 3 elements, A, B, C. Set B with 4 elements, where A is actually a subset of B. It's A, B, C right here, and an extra element D. And C is a set that has a new element E in it, but also contains A and B. We'll say that R is the relation A, A, D, B, C, C, A, and C, D. If we consider the Boolean product, MR with MS, the matrix representing R, or MR with the matrix representing S, the matrix representing R is going to be 1, 0, 0, 1, because A, is in the relation. And it is A, B, C, D, that these columns represent, and the rows represent A, B, C. So A, is in this relation, and A, D is in this relation. B, C is the only element starting with a B in this relation, and C, A is in the relation, and C, D is in the relation. Take the Boolean product of this matrix with the matrix MS, which is the matrix representing this relation. So this is going to E, A, B, and it's going from the set A, B, C, D. A, E is in the relation S. No other elements starting with A. B comma E is in the relation S. No other elements starting with B. C comma A is in the relation, and C comma B is in the relation. And lastly, D comma A is in the relation. Oops, I just realized I have a slight typo here. Sorry for the confusion. C comma B is in the relation, which is this one, and C comma A is in the relation. Again, the order of listing doesn't matter, but you got to make sure that you're consistent in terms of representing this as a matrix. And so the resulting matrix that we end up getting the rows are going to represent A, B, and C for the set A. The columns are going to represent C, which is E, A, and B. The A-eth entry is going to be this and this, or this and this, or this and this, or this and this. Because you have 1 and 1 here, and an or, that's going to be 1. And you can go through and compute the other values relatively easily to get that it's going to be this matrix right here. Which is the matrix that represents the relation A comma E, A comma A, B comma A, B comma B, C comma A, and C comma E. And if you remember from this example we did before, this is exactly the relation S composed with the relation R. And the way that we determined this before was visually, or we drew down the picture. I'll make this a little bit bigger so that you can see. This first set of arrows right here represents the relation R, which is AA, AA, AD, BC, CA, and CD is the relation R. The relation S is the relation AE, BE, CA, CB, and DA. And the composition is all of the ways that we can get a path directly from set A into set C. So for which there exists an intermediary element. And so this corresponds of AE, AA, BB, BA, CA, and CE, which is this last connection right here. So this is very convenient and allows us to use computers and by hand, if it's the matrices are small enough, to go through and compute this. And you can see very clearly that this is giving us information about the connectivity of elements between sets. So this idea is super useful in networking, and we'll see a little bit later on in what's called graph theory, so the theory of connected networks. In fact, I'll give the definition of a digraph or a directed graph right now, and we're not going to start jumping into graph theory too much just yet, but we will get into it a little bit later on in the course. So it's worthwhile to just give the definition right now. A directed graph or a digraph for short consists of a set V of vertices or nodes together with a set E of ordered pairs of elements of V called edges. Or arcs. The vertex A is called the initial vertex of the edge AB, and the vertex B is called the terminal vertex. So for example, if we have, say, a vertex set A, B, C, D, and an edge set AB, AD, BB, BD, CC, CA, CB, and DB. And so this graph can be visualized in the following way. A, B, C, and D as the vertices of the graph, we have A, B is an edge in the graph, directed edge, and we have AD is a directed edge in the graph. We have BB which is a loop from B to itself in the graph. We have an edge corresponding to BD. We have an edge corresponding to CA. We have an edge corresponding to CB. And we have an edge lastly corresponding to DB. And so this is the graph that represents this vertex set and this edge set. And specifically, really it's a digraph. It is a directed graph. So when we get into graph theory, we're really going to try and understand these a little bit better. But even now, it's a useful tool for visualizing a given relation, because we can very clearly see that E, the edge set of a digraph, is a subset of the Cartesian product of V with itself, which means that the edge set of a digraph is just a relation on the set of vertices. And this is a very, very powerful tool for both understanding relations and also understanding, if we prove something in graph theory about a digraph, we're actually proving something about a relation on a given set. Which very, very clearly shows the connection between mathematics and the theory of networks, and you can hopefully see very clearly this connection. So what I want to do to end the lecture is start talking about the idea of closing a relation, or my closure, and constructing an equivalence relation.